Graphing systems of equations. So we've seen that when we're looking at a system of equations, we're looking at two equations, or we could have more than that, but two equations that we are trying to find a point, a solution, that is true for both of them at the same time. So what we're going to look at now over the rest of the chapter is different methods of finding that solution. And we're going to start by graphing. So to do this, we're going to graph each, the directions are graph each system of equations and determine the number of solutions it has. If it has one, we're going to name it. So we know that a system of equations can possibly have one solution when those two lines intersect. They could possibly have no solution if those two lines are parallel to each other. And we could have infinitely many solutions if the two lines are actually the same line, which means that any solution that works in one equation also works for the other. So infinitely many. Not any of them, but there is an infinite amount of them. So let's take a look at actually creating a graph to find that solution. So we're basically just taking two equations and graphing them at the same time. Very straightforward. We're just looking for where they intersect. So I'm going to look at these two equations here, y equals x minus 3, y equals negative x plus 1. You'll notice that both of these are in slope-intercept form. That's probably going to be the easiest way to graph all of these equations. If we change each equation into slope-intercept form, we can use the slope and we can use the y-intercept to create that graph. So for my first equation, I know that the slope is 1. It's going to be the coefficient of x, and I know that the y-intercept is negative 3. For my second equation, I see that the slope is negative 1, and that the y-intercept is positive 1. I'm writing these out for your benefit so you see what I'm doing here, and you have this in your notes. Do you need to write these out in the future as you're graphing? You do not need to do that. You just need to get the graph correct. What I do want you to pay attention to as we're doing the graphs is that we are looking for a very specific point where these two lines meet. So when you create your graph, I want you to be a little more specific about where your line should be. Typically when we've done a graph, we've done 3 or 4 points, and then we've kind of extended the line to show where the pattern is. For systems of equations, when we're graphing to find a very specific point, we don't want to be that kind of generous with our line. We want to be very specific. So as we give our points here, and I'm using my slope to do that, I'm not creating a table. As I use my slope to find my points, I want to do as many points as I possibly can to find where those two lines cross. So I'm going to start with my y-intercept of negative 3, and I'm going to use a slope of positive 1. So a rise of 1, a run of 1. I'm going to put a point. Rise of 1, run of 1. Put a point. Rise of 1, run of 1. Put a point. I'm going to do a whole bunch of points on this graph. I'm just going to keep doing the points. I'm not going to do 3 or 4 and then just kind of draw the line, because we're human and our lines may be a little bit off, and the farther we get away from where we started, those lines will get more and more off. So I want you to continue the actual points that you draw to create the line. So I've drawn the line here, but I'm really looking at where the points are on this coordinate plane. Next I'm going to do my second equation. I have a y-intercept of 1, and I have a slope of negative 1. So I'm going to go rise of negative 1, run of 1. Rise of negative 1, run of 1. That is where they meet. So I want to draw the points, continue the points on both of the lines until I run into that place where they both intersect. Sometimes I may have to go backwards to do that. We can do that. Slope of negative 1, I can do a rise of 1 and a run of negative 1. Rise of positive 1, run of negative 1. I can go backwards once I've seen the pattern. Going backwards isn't really complicated to do. But I want you to draw the points until you see one point where one is drawn on the other. And then we can put our lines through those. So for this one, we see that this is consistent and independent. So I've come up with one point for my solution here. I've got one solution, and that solution is 2, negative 1. These are easy to check. I should be able to take this solution and put it into both equations, and it should be true. So if I put negative 1 equals 2 minus 3, yes, that's true. If I put negative 1 equals the opposite of 2, negative 2, plus 1, that works also. So these are very easy to check. There's no reason for you to have an answer that's listed incorrectly, because you can just go back and check them very quickly. All right, let's try a couple more. So I have y equals 2x plus 3 and 4x plus 2y equals 6. So this first equation is in slope-intercept form, so very easy to graph. I'm going to graph my y-intercept of 3 and my slope of 2, so rise of 2, run of 1. Notice here I might want to go backwards A rise of -2, a run of -1. A rise of -2, a run of -1. So we can go backwards with our slope. My second equation is not in slope-intercept form, so I'm going to do a little work here to get it into slope-intercept form. I realize that my y-intercept is 3, and there's where the two of these cross. So they cross at my y-intercept of 3. So this has one solution at 0, 3. Again, where they cross. And one more, I have x minus 2y equals 4 and x minus 2y equals -2. Neither one of these are in slope-intercept form, so I have to do a little bit of work to get them both into slope-intercept form. When I graph them, I realize that they have the same slope, and since they have the same slope, they're going to be parallel. We've talked about how parallel lines have the same slope. They're parallel to each other. They will never meet. So this particular systems of equation has no solution. So again, as we graph, please don't just use a couple points and then draw a line. Make sure you continue the points until you actually see the one place where those two lines actually meet each other.